Okay, I think it is best to start reasonably on time. There will be people trickling in as we are accustomed, but of course we also have to take care of our timing, so they can join at their discretion. Okay, today we have the third webinar lined up regarding the Nutri2Cycle Lighthouse Network. Now, we had already two interesting webinars over the last weeks. Last week we had two. The Nutri2Cycle Lighthouse Network is a demonstration network of 14 upscaled solutions that we are proposing and showing and validating in research, but also in practice and at the let's say relevant scale, at the farming scale. And in those we want to, of course, as is the Nutri2Cycle objective, aim to optimize the nitrogen, the phosphorus, and the carbon flows throughout the modern European agriculture. Today we have lined up four speeches, four presentations, which are related more towards precision farming. And maybe we can go to the next slide. So we have four presentations which are related more towards the use of equipment that can help us in precision farming and dealing with the heterogeneous nature of bio-based fertilizers, how to make it even better. So the recycling derived types of fertilizing products, how can we apply them in a good practice in reality? Before we dive right into it, one practical notice. Like the other two or the past two webinars, we will also be asking, and Margarita will be putting that in the chat. We will be asking to, as the presentations go along, fill in a little survey. It's not a lot of work. It's just to identify from your perspective the usability, the applicability, let's say the transferability of proposed technologies and presentations for your context in the region that you are in. This is supporting the Nutri2Cycle project because some of these solutions, actually all of the solutions, they are locally organized. They are a network of demonstrators. But we also are very curious what, for example, something which is proposed or being demonstrated or being validated in Italy, how applicable that is also, for example, in the Netherlands, Ireland, and so on. So do go to that link and fill in your perspective of the transferability of proposed techniques towards your specific region. And that will help the Nutri2Cycle project, so you can contribute there. Okay, so then without further ado, I would like to go to the first presenter, and that is from Italy. It's Massimo Zilio from the University of Milan in Italy, and he will be focusing on using digital precision agriculture and no-tillage, focusing on the organic matter stocking in an area which is characterized by lack of it. Now, Massimo is a research fellow. He graduated in biology at the University of Insubria in Italy in 2014 and obtained his PhD in agriculture, environment, and bioenergy in 2017. And since 2018 has been working on circular economy in agriculture, focusing on the analysis and use of bio-based fertilizers and their environmental impact. So, Massimo, the floor is yours.
Thank you, Eike. Good morning. Good morning to all. I'm sharing my screen. Okay, let's start. I'm showing you our results of these 3 years of experimentation in open field about our solution. First, a very fast reminder of the solution. This is based on an anaerobic digestion plant with a stripping system for nitrogen. The feed is mainly municipal sewer sludge, and the process is a thermophilic anaerobic digestion that produce mainly three kind of products. A digestate rich in organic carbon, very stable, with a low content of nitrogen and a good content of available phosphorus. This is considered a soil improver. An ammonia sulfate that is a nitrogen fertilizer rich in ammonia nitrogen, and the biogas produced by the plants is almost all used to feed the power of the plant. This is a little representation of the system with three consecutive digester that produce digestate, the stripper, the ammonia stripper that produce ammonium sulfate. But let's start to show the data, the results of our experimental fields. So we carried out a 3 years of experimentation in open field in the northern of Italy, in the Po Valley. Here we have the plant and the two experimental fields, one with wheat and one with rice here. Each of them had three treatments compared: a chemical treatment, a digestate treatment, and a non-fertilizer control. Later we will see each of these, what's meaning. The digestate in particular was a low nitrogen digestate injected in the soil at 10 centimeters. The experimentation carried out for 3 years and is also now ongoing for the fourth. We use obviously minimum tillage techniques and precision agriculture. Here the experimental plan for both rice and wheat, we compared three strategies: the digestate fertilization with digestate produced by the plant in pre-sown and ammonium sulfate in top dressing; the chemical fertilization strategy with commercial urea in pre-sown and also ammonium sulfate in top dressing. For wheat, the same, digestate compared with urea. Each of these three treatments was in triplicate plots. Now, in this moment, we have these data. We have also other analysis ongoing. Today I will show you these three groups of results: the change in soil characteristics after 3 years, the gaseous emission in atmosphere, so the environmental impacts, and the agronomic performances. Let's start with the change in soil characteristics after 3 years of experimentation in open field. In each of these slides, we will see in each graphics a comparison between the values of 2019, so before the start of all the experimentation in white, and the same soils after 3 years in 2022 in gray. Okay, in this slide we see the pH of the soil. You can see the NS symbol here is meaning not significant differences. So for this, for the pH for both rice and wheat, we didn't see any statistically significant variation after 3 years of experimentation for all our soils. We can only see that the wheat field is more heterogeneous in pH, but the change in these 2 years were not significant. So we can see that in 2 years we didn't causes any changes in soil pH. For phosphorus, we now have the values of available phosphorus. We are ongoing the analysis of more in-depth analysis of the speciation of phosphorus that we can have ready in the next months. But for available phosphorus in 3 years, we didn't see any differences, both in rice and in wheat. So we didn't see any accumulation on or any depletion of available phosphorus in our soils. But let's see the interesting results that because we instead see some differences for total nitrogen in soil, because here in red we see that in rice paddy in our field, the use of digestate causes an accumulation, a statistically significant here accumulation of total nitrogen in our soil. We see that the tendency seems to be an increase for all the soil in rice paddy, but the only really significant after 3 years is for digestate. So the use of chemical for now doesn't cause an accumulation of nitrogen. This for digestate probably is due to the high content of very stable nitrogen in the digestate. For wheats, no difference. We saw no difference. Okay. And let's show also the organic carbon, our results for organic carbon. Here, the same, we saw an accumulation of organic carbon in only for rice paddy in digestate in the digestate plots. So in the soils fertilized with digestate. Again, this probably is due to the high carbon content of the digestate that it is very stable. For wheat, in 3 years we didn't saw any accumulation for now. And now the part about the gaseous emission in atmosphere, so more regarding the environmental impacts. Here we measuring first the odor emission during spreadings, because yes, it's not the most important parameter for seems to be not the most important parameters for fertilized, but could be important because you can have the better fertilizer in the world, but if it emits a lot of odors or smell, probably people will not use it. So it's important that also the odor emission is acceptable, and also the odor emission is a good indicator for the stability of a biomass. And we measured the odor emission for the rice field in our 3 years of experimentation during the spreadings in pre-sown. And we saw that there is some variability, is normal for this kind of data. Urea shows the chemical shows the higher variability. This is normal for urea because the odor emission depends a lot by the moisture of the soil in the moment of spreading. Digestate was more stable in odor emission and was low and always comparable with the non-fertilized. On average, in 3 years, we can see say that there was no really differences. Yes, strong variability that is typical for any gaseous emission, as we will see, but not really statistical difference. Now ammonia. This is a very important parameter for environment. We measured ammonia emissions in 80 hours after spreadings in per zone for 3 years. In this graphic, we see in green digestate, in red chemical, so urea in per zone. First thing, very variable data. As I saw, as I said, is typical of gaseous emission. In 2019, both chemical and digestate emits almost nothing in the first 80 hours. In 2020, digestate emits more ammonia than chemical. In 2021, reversed. The chemical emits more ammonia than digestate. This depends all by the environmental condition in these 80 hours, condition of atmosphere and soil, because the fertilizer didn't change in these 3 years, and also the technique of fertilization of spreadings didn't change. On average, in 3 years, we can say that it's not possible to see any real tendency, any real difference, because digestate and chemical on average emits similar amounts. This also show how is important. That is very important to repeat this kind of analysis for many years to see if there is a real tendency, or if the variability can change the data. So we can say that on average, in many years, that the digestate injection in soil doesn't emit more ammonia than urea, but depends a lot by the conditions. And the last gaseous emission, the greenhouse gas emission during the crop season. We carried out 35 measurements in 12 months, so in 1 year, starting from the fertilization in pre-sowing in 2021 crop season, and also for continuous for the autumn and the winter following, so for 12 months in total. And these are all the data. The most interesting, I think, is the nitrous oxide, because we saw some differences. First, as the previous gases, a lot of variability again is normal. In this case, we saw that obviously digestate and urea, but mainly digestate, emits more than unfertilized, because obviously we added nitrogen. Chemical and digestate are not statistically different, but there is a strong variability. For carbon dioxide and methane, no difference. So also the fertilized plots didn't emit more than unfertilized plots. This is probably because the carbon that we added with digestate is very stable, so didn't emit carbon dioxide. No difference between digestate and chemical treatments in the total of 1 year. And last, our results about agronomic performances. We have the yield of rice and wheat. Not all the years. We will have all the years in the future. We for now we had organized and make the calculation for these years. So is partial this data. But we saw that the data is stronger. We saw that we have obviously produced more using the fertilizer, both chemical and digestate, compared with unfertilized. and the production for both rice and wheat using digestate was very similar and statistical, not statistical difference, different from the chemical fertilizer. So using digestate, we didn't lose yield, didn't lose performance. So also this I think is important for a fertilizer, obviously. So in summary, after 3 crop seasons in full field, using the digestate of these plants, we saw an accumulation of total nitrogen and organic carbon in the soil fertilized with digestate, but only in for rice. For wheat, for now, no. This can be due probably to the characteristic of the soil that are different, obviously, between a paddy and a wheat field, and also obviously for the environmental condition that is very different because a paddy is fluid, and so also probably are different the microorganisms in the soil that process these elements. For atmospheric emission, so the potential of impacts, environmental impacts, we on average we saw no significant differences between the use of chemical fertilizer and digestate, with as we saw a strong difference year by year. And last, the yields using digestate, we obtained similar yields compared to the use of urea, both for rice and for wheat. So the digestate didn't causes a loss of performance. Okay, this is all. Thank you very much to all, and if you have questions.
Indeed, thank you for the nice overview. And indeed, if there are questions, do post them in the chat. We can pick them up at the Q&A afterwards. So
okay.
That is, of course, we would have a little time if someone would raise, but let's as a rule of thumb save the questions for the Q&A. I would also reiterate to the audience or people that have trickled in the meantime to look at the link that Margherita Genoa has posted. There we have a brief survey for you to fill in. Telling us a little bit about the usability, applicability, let's say transferability of proposed solutions towards your respective regions and parts in the world, or Europe, as we are of course interested in. Then the second speaker for today is from Portugal, from ISA, Paula Alvarenga. And Paula Alvarenga is assistant professor at the Institute of Agronomy from the University of Lisbon, so the ISA Institute. She works in environmental chemistry sector, integrating LEAF, which is Linking Landscape, Environment, Agriculture and Food Research Unit, and the associated laboratory Terra. She has a PhD in environmental engineering, graduated in chemical engineering. Her R&D activities have been focusing on soil pollution and remediation, phytoremediation and the use of bio-wastes, and other organic matrices such as soil amendments. And now within the Nutri2Cycle project, her attention is focused on both sides of the agronomic valorization of animal slurries and manures. Benefits of nutrients and organic matter cycling, and potential risks to the environment. So, and today the specific topic is on the use of poultry compost and Pixelary to replace mineral fertilizers as a basal fertilization and maize crop. So, Paula, I invite you to turn on your camera, and the floor is yours.
Can you hear me?
Yes, we can.
Okay, so just a moment, please. Can you see now my screen?
Yes.
Okay, so thank you. Good morning, everyone. Thank you for the presenting me, Eric. I'm going to talk a little bit of our experiment that we have assembled with the collaboration of a farmer, of a big farmer. And in this experiment and with this farmer, we wanted to evidence the potential of using organic amendments like Pixelary and poultry manure compost from chicken or turkey to replace mineral fertilizers as basal nitrogen fertilization in maize crop. It's not a new solution, but the novelty for the farmers is that we want to evidence that a fraction of the mineral nitrogen provided by conventional fertilizers can indeed be replaced by organic materials without losing yield. So instead of using these materials in addition to mineral fertilizers, because some of them make that, but we want to evidence that it's possible to replace them. So the total and applied using the organic materials can be calculated once the materials are analyzed, and mineral nitrogen fertilization can be supplemented later during sowing, weeding, or irrigation to level the total nitrogen applied to the crop and using precision agriculture tools. The experiment was performed, as I said, with the head of a commercial farmer. Is the owner of exploration called Quinta da Solda in central Portugal, Azinhaga, one of the most important maize farms in Portugal, over 500 hectares of maize. The farmer is João Coimbra and is here considered a model maize producer. He uses a lot of precision agricultural practices, and he has indeed a very good experience and is able to obtain good yields, and is always he wants also to help academia, so he's a very good is very helpful. We have used 3 different agriculture fields from the farmer, and we have installed our experiment in each of these experimental fields. One site at the sandy soil with lower organic matter content, and at this site the farmer usually applies organic amendments in a yearly basis to improve soil quality. Uses at that site conventional agricultural practices. At site 2 is a loamy soil. It's a better soil with higher fertility parameters. No history of application of organic materials, and at that site the farmer uses conventional agricultural practices. A third site was installed in a field where the farmer uses direct seeding for over more than 15 years. It has a higher organic matter content because it has been increased in recent years. No history of application of organic materials. At each of these fields, 3 subplots of approximately 1 hectare each were installed in strips, as you can see over here in the field, and to test different applications of the materials we wanted to test. We test as basal fertilization with Pixelary, with poultry manure compost, and a control with mineral fertilizer. The Pixelary and the poultry manure compost were applied to provide the equivalent to 90 kilograms of nitrogen per hectare as basal fertilization, and the control to provide 60 kilograms of nitrogen per hectare in site 1 and 2 with conventional tillage, and 160 kilograms of nitrogen per hectare in site 3 with direct seeding. This is the usually practice of the farmers. This basal nitrogen fertilization would be complemented with top dressing or with fertigation in order to supply 300 kilograms of nitrogen per hectare. All the other operations regarding phosphorus and potassium fertilization, herbicide application, irrigation was the same used by the farmer in the whole field. So there were no differences in the other applications. Here you can see the slurry application that was performed. Here it's very evident in the field. And in fact, one important interest of these experimental sites were to use them in the scope of the Nutri2Cycle project to evidence how the application of these materials, both solid materials and liquid materials, are possible, the costs, and which companies can provide these services in order to the farmers can be persuaded to use these techniques. We had indeed some demo days explicitly to the producers, to the farmers. Another thing that we wanted to evidence, because the farmers sometimes are afraid of using these materials because of the legislation, we wanted to evidence the safety use of these materials, considering the existing legislation. And in Portugal, we have just released a new legislation in February 2022 on the agricultural valorization of animal manures and derived materials, which is most precautionary regarding heavy metal content. And we have analyzed the materials that we have used in the experiments, both turkey manure compost, chicken manure compost, and Pixelary. And all the heavy metals that they contain are lower than the legal limit in the legislation. So it's safe to use these materials regarding the accumulation of these heavy metals in soil. Even for zinc, that is the one with the more restrictive, it has a high content of zinc, but lower than the legal limit values. So no problem from this side, and this is very important to evidence to the farmers. What the materials were applied, considering what we thought it was the total nitrogen content in the materials provided by the producers of those materials, the Pixelary and the poultry manure. So we have applied based on a previous an estimated amount of nitrogen, and we have applied 32 cubic meters of Pixelary per hectare and 10 tons of compost, poultry manure compost, fresh material per hectare. Afterwards, we have analyzed the materials, and considering the total nitrogen concentration in those materials, we have calculated the total nitrogen applied in this basal fertilization. And we can see that the total amount of nitrogen provided by Pixelary and by poultry manure compost is higher than the total provided by the mineral fertilization. But then again, this was intentional, because the total nitrogen, it's different from the available nitrogen, and we did not want to have problems for the early growth of the culture. After, when sowing, more nitrogen was applied with the usual practices of the farmer, and the total nitrogen application was leveled in all the plots during weeding. So in that case, during weeding, the nitrogen applied was not the same in all the plots, and using precision agriculture practices, this is possible, and it was different in each of the plots, and the farmer allowed that. So at this moment, the total nitrogen applied was more or less 160 kilograms of nitrogen for hectare, and afterwards, during fertigation, more nitrogen was applied until a total of 300 kilograms of nitrogen per hectare. So if you compare this figure with the total nitrogen applied with the organic materials in the basal fertilization, we can see that approximately 30% total nitrogen was indeed applied with the manures, so saving approximately 30% of the mineral fertilizers application, and this can be considered a replacement of these materials in 30%. We have performed the soil sampling and soil analysis, which is still ongoing. We have compared maize yield in the different crops. We have measured SPED, have made SPED measurements, and we are also looking at the nutrient use efficiency. And we have collected greenhouse gases in chambers, in these static chambers, using this technique for the whole experimental season from April to August. At the beginning, more frequently, 3 times per week, and then weekly until the end, until harvesting. We have collected gases and calculated in order to see if there are differences in the emissions of methane, nitrous oxide, and carbon dioxide from comparing the organic materials with the mineral fertilizers. The results are still being evaluated and obtained. So here I'm only going to show you some of the results that we had for now and treated. We have made some SPED measurements in the different plots. Here are the results for the loamy soil in the Melhorada field, which is the soil with the better soil parameters. We have not had any differences in the experimental plots regarding chlorophyll content in the different plots, even when using when replacing the mineral nitrogen by organic nitrogen. Afterwards, before harvesting, we have evaluated the productivity in 2021, and in the next tables we can show you this productivity obtained in 2021 in comparison to that obtained in 2020 using the usual practices of the farmers. And we have the results for our plots: mineral fertilizer, poultry manure, compost, and Pixelary, also relatively to the conventional practices of the farmers in that field. So we can compare the variation of our productivity considering the previous year and comparing it with the farmer productivity. And in this field, Melhorada, with the loamy soil, we can see that when using poultry manure and compost and Pixelary, we have had a slightly higher increase in productivity, higher than that obtained with the conventional practices of the farmer. And when using mineral fertilizer, this field was indeed the one with the better performance for the organic materials and the better performance in the whole experiment, because at this site we can have very high productivities, almost around 20 tons per hectare of maize produced. In the other field, where there is a direct seeding practice, the productivity is lower, is around 60 16 tons per hectare, and so the overall maize yields in direct seeding are lower, but we have also had an increase from 2020 to 2021, not so good in all the organic treatments, but indeed the higher variation was obtained after Pixelary application, with higher productivities, even higher than when using the conventional practices of the farmer. The worst results were obtained in the sandy soil, comparing the results in our plots with the conventional practice of the farmer. So here the productivities here are higher than when using direct seeding, but the results with the organic materials were not so promising, but then again not so bad after all. This experimental site is indeed very heterogeneous, was the first to be sowed, and it rained a lot in the following weeks, so we have faced some leaching of the materials, and with differential leaching in the different plots. We have to analyze those results, also looking at these climatic conditions. The yield increased from 2020 to 2021 after Pixelary, and for the organic materials, the results were the best results were obtained for the Pixelary application. Looking at the greenhouse gas emissions, we have obtained the cumulative gas emissions from April to August for carbon dioxide, nitrous oxide, and methane. We have calculated these in the three experimental fields. In these graphics, we have in green the emissions obtained with the mineral fertilizer application, and we have put that as 100% emissions, and then the emissions of the gases with the use of poultry manure compost in blue, and Pixelary in yellow, and we can see if there is an increase or a decrease relatively to the use of the mineral fertilizer. It's the way these graphics can be analyzed. So they are not yet statistically treated. We are sorry for that, but we are now treating all the results and looking at the results, and we hadn't had the time to do that. But in most cases, we can see that the poultry manure compost emitted more gases, more carbon dioxide, nitrous oxide, and methane in the direct seeding than the other materials that were applied. On the other hand, the Pixelary nitrous oxide emissions were always lower than when using the mineral fertilizer, and it's important to say that this gas is much more potent than CO2 emissions. Both organic materials led to a high increase in methane emissions only in the direct seeding, but there the emissions were quite high when using the organic materials. So for final remarks that are possible now, because we are still ongoing in this study and evaluating in the results, so they are only preliminary results. We're sorry for that. This experiment evidenced some benefits and some limitations related to the use of these organic fertilizers for maize fertilization. But they evidence that it's possible to close nitrogen, carbon, and phosphorus loop in maize crops when using these materials. For nitrogen, approximately 30% of the mineral nitrogen fertilizer can be replaced by organic nitrogen, an organic nitrogen source without losing yield, and that is very important to evidence to the farmers. We are able to close the loop of these slurry and compost nitrogen by using them in these crops. For carbon, both compost and slurry contain a significant amount of organic matter that will enrich the soil organic matter and most surely will allow an improvement in soil parameters that will are evaluating, but they have that it has that potential. And for phosphorus, the organic materials also provide phosphorus to the soil, ensuring a closure also of this P cycle. We have not considered that to decrease also the phosphorus mineral fertilization, but we intend to do that in the future and also evaluate that possibility to avoid extra application and save some of the phosphorus mineral fertilizers that are applied. So we have evidence that, and we think that it's very important because it was made in the fields of the producer itself, and he has collaborated, and it can be used as a testimony to the other farmers. So thank you very much for your kind attention. We thank for the possibility of presenting this work, and we prepared for your questions. Thank you a lot.
No, thank you for presenting. It's very nice, and indeed there are questions popping up in the chat. You can already have a look at it, but we can also go over them briefly at the end in the Q&A session. Now, moving on to the third speaker of the day, and moving from Portugal to Hungary, we have Zoltán Hajdú. If I pronounced it your last name correctly, Zoltán. He is a manager of Soltup research and consultancy company, and has also participated previously in the AEP Agri focus group on nutrient recycling, in which quite a lot of members of the Nutri2Cycle project were involved. Today he will be talking and telling us a little bit more about comparison of different precision technologies used in plant cropping systems, having in focus sensor technologies. So Zoltán, I see you already turned on your camera, which is good. So the floor is yours.
Thank you, Eric. Good morning, dear colleagues. So in the next minutes, I would like to give you a short presentation about precision technologies used in plant cropping systems, having in focus the sensor technologies, and we focus it in this demonstration on those technologies which have in focus to assess the crop's nitrogen status. The next one, please. As we know, in plant cropping systems, opposite to previous practices, the point of soil and plant sampling in the precision agriculture, technologies that obtain information on the soil health status and vegetation, nutrient and water supply through remote sensing are becoming more and more widespread. The advantage is that with the help of remote sensing, we get a more reliable and more detailed view of agricultural plots, which greatly helps farmers to take quick and site-specific decisions. In this sensor demo, the main objective was to assess the environmental and technological benefits of different precision technologies in order to increase the nutrient uptake and reduce the nutrient losses. The demonstration trials we performed since 2019, when we assessed the nutrient uptake of crops under different soil conditions using tractor-mounted sensor technologies. Actually, two systems were taken in consideration the Yara and the Green Seeker, technologies, and those were assessed at 3 Hungarian farms. From 2020, a new demonstration was introduced, which targeted the utility of using drones for the unmanned area vehicles in nutrient management. And this is actually not a farm scale, but in an experimental stage. But I will give you details later on. Among the sensor technologies, other possibilities and technologies are available which are not included in our demonstration. For example, the AgroSense, which is a wireless network of small meteorological stations and is based on Internet of Things solutions. The other is the AgroCares, which is a smartphone and tablet application based on near-infrared technology, which include camera system, GPS positionings, and other tools which are easily portable and have a high computing power. The next one, please. So going back to the tractor-mounted sensor, we can say as general advantages that more uniform application of fertilizer is possible, which means that the fertilizers are placed in the right place and in the right amount. Therefore, it is possible to reduce the soil nutrient potential diversity. The maps which are created and I will present on the future slides, the maps which are prepared for nutrient management can be used also in plant protection, for example, in pesticide spraying, or in the variable but not only Hungary, also in Europe. From point of view of environment, using sensor technologies it's possible to have reduced nutrient leakages and runoffs, and after several years the soil heterogeneity is reduced. From point of view of economics, of course, there are savings of fertilizer costs, which is a positive one. But as negative, if we can say that is a negative impact, is the investment in the sensors. During the last 3 years, we performed also a life cycle assessment for these sensor technologies. And we assessed in the study that there is no significant difference between the sensors and no sensor technology. The next, please. Margarita, please, the next, please.
You should be able to see the next one.
Okay, thank you. So how the tractor-mounted sensor actually works, we can divide 4 major steps. The first step is the field scanning, when these presented technologies, Yara and Green Seeker, both use the normally the difference vegetation index, which is a recording, which is taken in calculation. The infrared and absorbed red light reflect differences and can have values from -1 and +1. Data or recorded having ranged to the -1 mean that is a less reflected light, meaning there's less reflected chlorophyll, so that means less vegetation. In an indirect way, it means that less nitrogen provision for the plant. If the values are close to the +1, means that the reverse case, so is a good provision of chlorophyll, it's a good provision of nitrogen. The second step is that these raw data taken by field scanning are processed in the office. So fertilization maps are obtained based on the NDVR maps. And the fourth step is that based on the field level fertilizer maps, the tractor driver can fix the chemical fertilizer spreading machine. If we can compare the Yara and the Green Seeker system, we can say that maybe an advantage for the Green Seeker is that it's compatible to isobus monitors, all, and the sensor heads can be changed. The next, please. So in this picture, you have on the left side the Yara sensor, which is the yellow tool, the white tool mounted on the top of the cabin tractor, the white tool, and in front you see a GPS positioning tool as well. On the right side, you see the Green Seeker tool, which is mounted in the front of the tractor. And in some cases, farmers use also some complementary data to have a more broad picture on the soil nutrient provision. So in the bottom picture is a foliar tester, a Yara foliar tester, which is used by the farmer when the worker is going in the field and is taking leaf samples. The steps of the leaves are the data taken from these leaf steps are introduced in this tool. The tool is later on connected with the computer, and another map is produced. The next one. The tractor sensor tool has also a touch screen, which is mounted in the cabin, the tractor cabin, and the driver manages the required fertilizer machinery. And the hand over there on the left side of the picture is showing the tool, which is actually opening and closing the slot, which is regulate the chemical fertilizer on the distribution. Next, please. So these are the NDVR maps and the fertilization maps, which I mentioned. On the left side, you see the NDVR map having the colors from the dark green to the yellow one. The dark green means, of course, a very good provision of the soil with the nitrogen, and the yellow one meaning the deficit one. Based on this NDVR map, the fertilizer map is converted, which is actually a reverse of the NDVR, when we have the dark blue, meaning the areas where a larger amount of fertilizer will be applied, and the light blue, meaning that the areas where less chemical fertilizer will be applied. The next one, please. The next one, please.
The next one you should be able to see again.
I do not see it. Yes, in some cases, some farmers use also harvesting maps beside the NDVR maps. You see here for the same plot, an NDVR map on the left side with the yellow and the green colors, and the harvesting map on the right side. Where there is a similarity, of course, between the data. On the right side, the harvesting map, you see the dark green colors, which means that higher yield were harvested on that plot side, and the red one, the red color, indicates reduced amount of harvest. The next, please. So if we want to compare the tractor sensors with the drones, which is a future perspective in the Hungarian farming, but also in the EU farming systems, we can say that in both cases, the NDVR maps are used, but we can say also that differences are much more larger. For example, if we consider the tractor sensor technologies, we can say that the recordings communicate directly with the fertilizer spreader control unit, while the drone recordings must be processed. The tractor calibration maximum and the minimum values are performed in advance, and maybe a disadvantage for the data recording, the second one for fertilization, which is time and fuel costs consuming, and also the double root induced soil compaction. If we can take the drones, we can say that larger areas can be surveyed per day, and the NDVR data are available immediately. But there is a more complicated case because the area need to be flow with the drones many times. The data need to be processed, and only then can the fertilizer machinery be fixed. Is a peculiar thing here with the drones. If we have variety testing, then should be taken in consideration that for the same species, different colors and so different color reflectances can occur. The next, please. So what we can say about the drones' advantage in general, that the drone market is an expanding one, and also the software, which is for data processing, are available in a large number. The advantage of the drones is that they can be used even in the different weather conditions, even in cloudy areas, if they are below the flight requirements. And they can provide us real-time information at a relative low cost. Considering the resolution, for the drones, the resolution are a few centimeters opposed to the satellite pictures. They can be used for different agricultural crops, for example, vineyards and orchards. And there is an innovation potential in it, because in the future it's possible to have a direct communication between drones and tractors if the tractor system will be a full automatic one. The next one. So why is interesting to the drones? Why are so for the future? Because they can give us, as was mentioned, real-time information about crops and status. And they can be equipped with several tools. Some of them is the multispectral cameras, which operate in 4 or more color bands. thermal cameras operated at different resolutions. As I was mentioned, different softwares are available on the market, and we can say, at least on the Hungarian conditions, that 90% are DJI type, which are made in China. The next one. So as mentioned in the beginning of the presentation, that from 2020 we used a new demo which focus on the validation of the pictures taken by these drones and eddy covariance based on the evapotranspiration. On the screen you see the different tools which can be mounted on the drones, which are thermal cameras, GPS chips, Wi-Fi high box, actually a mini computer, normal cameras or multispectral cameras, and of course the GPS positioning systems. Next, please. So the experiment is about that how can be compared the production, the data taken from eddy covariance procedure, which is actually a meteorological station which measure vertical turbulent heat fluxes and also the wind speed, orientation, radiation, gas concentration, and temperature, and give us output data at ecosystem respiration, gross primary production. How can this bunch of data used with the pictures and the data taken from with the drones? The next, please. And this is an evapotranspiration map provided by this eddy covariance station. Next, please. And the comparison with the data of obtained in eddy covariance measurement, which is a soil-based measurement, and those taken by drones with those mentioned tools, the result is that there is a strong correlation between the gross primary production and the evapotranspiration rates. So that means that in the future, drones can be used for evaluating the nutrient provision or CO2 production, carbon balance of soils, but also can be used those maps provided by the drone mapping for plant protection, irrigation planning, plant variety testing, or the emerging technology in variable rate fertilizer application. The next, please. So in the left side in this picture, this slide, you have the drone normal camera, which is, you see the plant rows. And on the right side, you see the auto photo, which is created. And based on this auto picture, the fertilization map can be done. Next, please. We had also during the project some demonstration and communication activities. Video film was presented, was made for the tractor-mounted sensor technology, and is available on the project website. We published it in an article on the drone technology in the Hungarian Agro Forum in this year, February. And we are planning, actually the raw material is available, the second video with the drone technology using the evapotranspiration measurements. Next, please. Thank you for your attention, and I'm pleased to answer if questions are. Thank you very much.
That was indeed the last slide, and maybe for completeness sake, also adding that on the Nutri2Cycle website, we are currently developing a dedicated spot for the 14 demonstration, the demonstrators of the network. So you will find the information there soon, with videos, with background materials, and with a nice map that you can hover over to find the different demonstrations of the different countries. Then again, asking or inviting for questions in the chat. That's one. Second, repeating that there is also this survey. If you scroll back on the chat to the first or one of the first messages that was given by Margarita, you will find a link to the survey for transferability or adaptability of those techniques in your respective regions. Then we are already at the very last and the fourth and the very last speaker of today, and also of this webinar series of 3. So indeed, let me invite Chantal Hendricks, who is a researcher in soil and climate for the Sustainable Soil Management Group at the Wageningen Environmental Research in the Netherlands. Her research mainly focuses on modeling nutrient and carbon flows of agricultural systems at different scales. Within the Nutri2Cycle project, she coordinates the innovative solutions that are developed under the research line that links to tools, techniques, and systems for higher precision fertilization, which is, of course, also the topic for today. And together with ZLTO, that is the Farmer Association in the Netherlands and also partner within Nutri2Cycle, and Ghent University, she is co-leading one of the solutions, which then today is topic of the speech. Now, Chantal did her PhD at Wageningen University in research, where she bridged the supply of and demand for soil data in land uses analysis. And during her postdoc research at the University of Oxford, she studied the relationship between the use of agricultural insecticides and insecticide resistance of malaria vectors in Africa. So that's a completely different topic and not for today. Might be interesting as well, but not for today. So today we will be talking about trial potato growing with refined pig manure fractions at the border, actually, of the Netherlands and Belgium. So Chantal, the floor is yours.
Yes, thank you very much, Eric, for the introduction. I'll share my screen. Yes, all right. Well, I hope everyone is still there because it's almost 11:15 already. So, this is the solution I'm presenting today. It's about the trial potato growing with refined pig manure fractions. And as Eric said, it's not only me organizing this demo. It's also the University of Ghent who is involved, and a southern agricultural organization in the Netherlands called ZLTO. So what we are doing in this trial is that we are analyzing the environmental and agronomic effect of different bio-based fertilizers on potato growing in sandy soils. So this is of importance because, 3 things. One is that we need to prove that bio-based fertilizers can be used safely in agricultural soils. The second one is assessing the potential of closing nutrient loops, which is essential of Nutri2Cycle. And the third one is to stimulate the adoption of new techniques. So this was a very nice collaboration between livestock farmers, a livestock farmer, an arable farmer, but also with the manure processing industry. So there was a pig farmer involved. Well, the pigs, they produced the manure, and on that pig farm, the manure was processed into bio-based fertilizer products. These products were applied on the soil of this arable farmer. This is a potato farmer in the Netherlands, a very big one, and it's also very interesting because he is aiming for becoming a farm of the future, and he is one of the, he's the Center for Precision Agriculture, so the Practice Center for Precision Agriculture. So he is teaching a lot of other farmers how to use precision agriculture and how to apply different techniques. So interesting to see is that the effect of the nutrient use efficiency. So how can we increase this using precision agriculture? And interesting is that the potato peel ends up as pig feed again. So then it's a quite closed cycle. So as Eric said, this is part of the research line 3, tools, techniques and systems for higher precision fertilization. And well, as you can see on the map of the Netherlands where the bio-based fertilizer is produced and where the bio-based fertilizer is applied. As you might know, in the Netherlands, we have a surplus of manure. So quite a lot of manure is exported to neighboring countries like Germany, France. So using the bio-based fertilizer close by will result in less CO2 emissions due to transportation of the manure. So a short setup of this experiment, we compared 3 different bio-based fertilizers. One is the liquid fraction of digestate, which is a less refined product, still having nitrogen and potassium in there. But you can refine this product further to ammonium sulfate or to potassium concentrate. So the manure processing industry is interested in how this refinement, you can imagine the more refined the product is, the more it costs to produce, whether this refinement will result in higher crop yields or improve the crop quality. While the arable farmer is really interested in using these products because can we use, for example, a less refined products, or do we need to have these products that look quite similar to mineral fertilizers in order to produce the same amount and quality of potatoes? So what we did an environmental evaluation. So how where we looked at the N release rate. We did that in the laboratory in Ghent. We measured the greenhouse gas emissions after soil application, which was also done in the laboratory. We analyzed the fertilizer replacement value in a netting tunnel. And we did an agronomic evaluation in the fields where we tested the potato quality and quantity. And in the end, we made a comparison of product application costs of the fertilizers. So first we analyzed the soils, the soil of the farmer and the fertilizers. So for the laboratory experiment and the pot experiment, we used the soil of the farmer to be able to compare it. So important to see is that the fertilizer recommendation for potato growing was 310 kilograms of nitrogen per hectare per year. So that's quite a lot. So yeah, what we applied in the field, we applied these 310 kilograms of nitrogen. So the fertilizer characteristics are mentioned here, and important to say is the difference in nitrogen in the liquid fraction of digestate and ammonium sulfate. You can imagine that if you apply this in the field, the liquid fraction of digestate needs to have a huge amount of products to receive to apply the same amount of nitrogen compared to ammonium sulfate. And as you see, the sulfur and pH of the ammonium sulfate is an indication. Well, we need to be aware of this, that if we use this in a long term, it might acidify the field. So these are some results. The nitrogen mineralization rate was tested in a laboratory, as I said, and you see that the liquid fraction of digestate and ammonium sulfate do not differ that much and also compared to the can, so the mineral fertilizer, it's quite similar, and that's probably because of the high ammonium and total nitrogen ratio in the products. So we also tested the greenhouse gas emissions after soil application, and you see immediately that the mineral fertilizers produce much more nitrous oxide emissions compared to the other products. That's because of the rapid hydrolysis of products after application. We also test the CO2 emissions, and it depends on the initial organic carbon content available in the bio-based fertilizers and the mineral fertilizers, how much emissions you will get. And the methane emissions, as you see, they are negative, and that's probably because there are aerobic conditions resulting in a reduction of the methane emissions. So then we continue to the fertilizer, to this netting experiment where we tested the fertilizer replacement value. So what we wanted to test is how well are these fertilizers perform in comparison to mineral fertilizers. So what we did, we took several percentages of the advised amount of nitrogen, and we applied these in mineral fertilizer form to the plants. And besides that, we also applied 40% of the advised amount of nitrogen as liquid fraction and 40% as ammonium sulfate to see how it will respond. So in the right figure, you see a curve where you see the mineral fertilizer on the x-axis and the potato yield on the y-axis. And because you use these different percentages of advised amount of nitrogen, you can draw this curve and you can plot the performance of the liquid fraction and the ammonium sulfate on this line. And so you can calculate the nitrogen fertilizer replacement value. So this resulted in a nitrogen fertilizer replacement value of 1.04 for liquid fraction and 1.13 for ammonium sulfate, which was higher compared to, so it's above 1. But if we are calculating the nitrogen fertilizer replacement value based on the nitrogen uptake in a potato tuber, this value resulted in 0.5 for liquid fraction of digestate and 0.6 for ammonium sulfate. But we took the potato yield because you have a higher amount compared to the nitrogen uptake in potato tuber was very low. So that's why we took the potato yield. So, and then in the field trial, we made different plots, as you can see in figure A. So we had these treatments with mineral fertilizer and manure, liquid fraction and manure, ammonium sulfate and manure, or plots where only liquid fraction or only ammonium sulfate was applied, so no manure. And there was a control plot where no nitrogen was applied. The other minerals were kept, were given in the amount that was advised by the laboratory. So as you can see, you see in figure B the electrical conductivity of the field, so the soil variability, and the weighted difference in vegetation index is given in figure C. So figure C is taken during this growing season, and you can see a little bit the red spots here. I hope you can see my mouse, where you can see the control plots popping up. And in figure D, you see the thermal heat map, where you can also see that these plots face some stress. And in the figure E, you see the average potato yield. So taking the average potato yields, we could not come up with a strong conclusion, except that the potato yields were quite similar among the among the different plots and among the different treatments, except for the control. The control showed lower yields, and also the size of the tuber was smaller. So in average, yields were comparable, and the potatoes of all fields had an underwater weight of between 70 and 80%, which is a threshold for potato farmers to get a good price for the product. And we saw that the liquid fraction of manure, liquid fraction of digestate in combination with manure, that 95% of the tubers size was below 5%, which was highest compared to the other treatments. And the control even showed higher amount. I think it was about 75% of the tuber size was below 5%. So after harvest, we also took soil samples of the topsoil and subsoil to see the nitrogen residue in the soil, which can cause leaching in the end. And we saw that quite high amounts or in fact, extremely high amounts of nitrogen residues were still in the soil, which was probably because the recommendation for potatoes was 310 kilograms of nitrogen, while the farmer told us that normally he is applying 270 kilograms of nitrogen. So here are my conclusions. Well, on the short term, it was safe to use these bio-based fertilizer as a replacement for chemical fertilizer. We saw a good result of the nitrogen fertilizer replacement value, for example. We didn't see strange things in the amount, in the crop yield or in the crop quality. So that are indicators that these bio-based fertilizers can be used in potato growing on sandy soils. However, we don't know the long-term effects. So this was only a study for 1 year. Another thing is that, well, circularity would be stimulated when these bio-based fertilizers are listed as manure materials. Because what we saw during the trial is that, especially when we ask about the product cost and how much it costs to produce it, because there is a surplus of manure in the Netherlands, arable farmers get paid to spread their products on the field. So even bio-based fertilizer, which are still seen as organic fertilizers, pig farmers need to pay the arable farmer to spread it on their fields. So this is, an important message, I think. Besides that, the arable farmer also came up with some practical issues that occurred during the application of liquid fraction. One of them was the large amount of liquid fraction that needed to be applied on these small plots. So that was a problem, but also applying the liquid fraction or injecting the product in the soil during the growing season, because you have these rows where the plant is growing and there was no machinery that could be used for precision application of these liquid fraction during the growing season. And the last point is reducing the surplus of manure would stimulate the use of a fair pricing of the bio-based fertilizer product, as I said before. So evaluating this study, we have some remaining questions, of course, and one of them is this study mainly focused on the products, on the bio-based fertilizer products. So there is a follow-up project at the moment running where we look whether the manure or less refined bio-based fertilizers in combination with precision fertilization can be used. So the focus of this year is more on the precision fertilization. So in here you see the hypothesis. So at the moment, the application of Pixelary is equal all over the field, which can cause differences in leaching or differences in nitrogen uptake. So we will check whether the electrical conductivity can be used as an indicator for better precision agriculture, and also applying variable amounts of Pixelary, and whether we need to apply a low amount on those spots where there is a low electrical conductivity, or a high amount on those spots where there's a low electrical conductivity. That's the question. So that's really the hypothesis of this study. So I would like to finish with this figure where we show the general overview of the different of the use of primary resources, emissions to the environment, and resilience to climate change, and how this solution helps improving these three things. So that's it. Thank you very much.
And thank you for the nice presentation. And indeed, it is a good challenge at the moment. Also, well, you also touched upon Manure products and Manure criteria. Of course, the current focus of today is technology oriented, and how to deal with variable composition products such as derived from manure, and then using precision farming principles and techniques accordingly. What I would like to share also with the audience is that also on the policy side, the project is making recommendations and proposals and policy briefs, both in public consultations, so we have a policy working group to do that, but also in direct interactions, and amongst others via conferences like Manure Resource, which we have been organizing every 2 years, and in which we are also interacting with policymakers from the Commission and member states to push also the state of policy forwards. And Manure, which is, for those who are not familiar with the term, recovered nitrogen from manure, and Manure is in the aspirations to replace synthetic mineral fertilizers. Okay, so that draws to a conclusion the 4 presentations we had lined up for today. Let us go through the chat for some questions, if there were. Also, people that want to raise a question, please feel free to raise your hand if you want to, if you still have some questions that you did not share in the chat part yet. I do see, let me see, for example, first question from Zoltan towards Massimo. What was the amount of digistate per hectare used? Maybe Massimo, you could share a little bit on that.
Yes. Okay, start with the amount of digestate we used. I have the data. For rice, in rice we used moment, I have a lot of files. For rice we use 50.6 tons per hectares of digestate. This is the wet weight, so digestate. For wheat we used more, 22.2 tons per hectares of digestate. The composition, I see in the question, the digestate and nitrogen content. We published a paper with all the characteristics of this digestate. I can show you. I will share my screen here. This is the paper. Maybe I can add the reference of this paper to the slides later. So you will have in table 2 of this paper are reported all the characteristics of this digestate used also in this work. The total nitrogen content in dry matter is 77 grams kilos. So the 7.7%. Of this nitrogen, the 46% is ammonium nitrogen. And then Let me see the question, because there is a lot of questions
Yeah,
here.
there was another question as well, but I'll guide you through it. There was another question from Hongzen about what was included in the odor emission measurement.
Yeah, the measurement of odor emissions were in dynamic of olfactometry. I can show you the slide. This is another presentation, but the analysis was not molecule by molecule, but is analysis of the odor intensity. So we don't have the composition of the air of the odor. We simply sampled the air in open field during the measurement, and carried the air in this plastic bag at the laboratory, and a panel of people measure the smell. So it's only a data about the intensity of the smell, not the composition. So we don't have the composition of the smell.
Yes, maybe indeed elucidating that process. Olfactory units are still done with the human nose, so it's about the intensity. It's not about the chemical composition. It's really about when how long or how much must you dilute before you lose smell, and you have odor panels, people who are really good with their nose, as we say. Who do those olfactory unit calculations or determinations. So okay, might I also ask the people to conclude on their survey so that they get finalized, so that we can compile and use them. So do finish up on the surveys and submit. Then maybe a question from Zoltan towards Paula. What is the economic advantage of using compost and Pixelary per hectare compared to chemical fertilizer?
I have already put some data in the answers in the panel.
Okay.
We only have made that quantabilization in 2020 prior to our field experiment. The farmer made that account. He had the prices for 2020, which are not the same. And in 2020, with the mineral fertilizers, the amount per hectare was 497 euros for hectare. And for the solution with the mineral fertilizers plus the poultry manure compost, which the farmer usually buy it to apply in the sandy field, it is a total of 580 euros per hectare. So in fact, he has no economic advantage of using these organic materials, at least only accounting for the nitrogen. Perhaps if he also accounts for the phosphorus mineral fertilizer and discounts also that mineral fertilizer, you would have an economic advantage. But in fact, you see the application of the organic materials as indeed an advantage, despite the slightly higher costs of using that material, because it is see that application as an improvement in soil quality and a way of putting organic matter also and other nutrients that is not accounting for them. So this farmer, that is why he's an example, thinks that these applications, these advantages, despite not having an economic advantage of using it. Of course, for instance, if you use the prices that mineral fertilizers have nowadays, perhaps it would correspond even now to an advantage. So this depends pretty much on the prices of the market in each year. For the second question that he put at me, if the Pixelary was treated, no, that Pixelary was raw Pixelary, because this farm is in a geographical area where there are few pig farms. So there are no surplus of slurry, pig slurry, and the pig producer uses in its own farm. So this experiment only used the pig slurry just to have a comparison between those materials and to have an idea about the application also of Pixelary, because it's not, there is no surplus in that area. Of course, there are in different areas in Portugal, as in your countries, but not in that one. And in those in those areas, there are explorations which have separation and anaerobic digestion and so on. But geographically, at that site, we only had raw Pixelary. I don't know if it's enough, Eric.
Wait, I was muted. Yeah, I think so too. And you also responded in the chat, of course, elaborately. And of course, if Zoltan has questions, he can pick up via mail afterwards. If some things are not clear. There is a question also on the economics towards the drones. Let me scan that up from Yingzi Zan on the drone application and stationary sensors, whether there are economic data available for that. I think it might be a general question because, of course, several of you use this type of technology. So I'm not entirely sure whether we also have economic data available for this. I would assume so, because within the Nutri2Cycle project, we are also having an economic assessment, cost benefit assessment for the solutions. So the data is being gathered. I might understand that the people who are now presenting do not know these data by heart, but Yingzi, the data is being gathered and compiled, so it should be available if you want that for your particular research. Then I think we can come to a conclusion. I'm not sure whether Margarita, whether you have something to share on the transferability, or whether we leave that for now and send it afterwards with the rest of the documentation, considering we are now half hour beyond the dedicated time slots. Okay, we do. Okay. Just briefly touching upon this, we will also do a deeper analysis and also compile this data together with some other sources. But this indicates what you today have been considering as transferability of certain principles related to these solutions to your respective region. And of course, we will break that down in member state level so that we can make a more thorough investigation. So for the first discussion on using digistate and precision agriculture in combination, also focusing on the organic matter stocking, short-term transferability roughly around 50, and on the medium it's a little bit higher, so towards 66. And also for the poultry compost and Pixelary combination to replace mineral fertilizer, we see the same trend, roughly around 50 transferability on the short range, and roughly 69 on the midterm. Now, one thing that might be interesting when we are going to make a deeper investigation in this is that, of course, transferability is not only about technologically readiness, but also about economic and agronomic context. So things which might make sense in manure pressure regions might make less sense in more extensive agricultural regions throughout Europe. So transferability is not only about technological readiness, it's also about local context. Then maybe moving to the last two, or the next two, and the last two. Well, actually, we see that, but of course, it's not so surprising because the four presentation are quite similar, but looking from different angles and different field trials. In each cases, these were linked to manure and combination with sensor technologies. And we see that for all four, we have a similar breakdown. So also 3 and 4 have roughly 50 on the short-term transferability and about 76/70 for the medium-term transferability. So at the moment, we cannot derive more from that. We will have to do a more deep investigation, but we do thank you for your responses, as this will help understand the usefulness or the possibility to use technologies throughout Europe. Okay, I think without further ado, I will wrap up for today, and this also immediately ends the webinar series of 3 webinars we had dedicated to present a little bit more on the ongoing demonstrations that we do have throughout Europe. Thank you for listening in, and of course, feel free to keep in touch either via our social media or our website. Bye-bye.
Bye-bye, Eric, dear colleagues. Bye-bye.